Hello again, and welcome to our lecture on polar coordinates. Polar coordinates are a new way to describe the position of a point in the plane. You remember we have Cartesian coordinates, the XY pair. Well, now we'll have a different pair of coordinates, r and theta. And r will be basically the distance from the point to the origin. That said, I'm going to modify that a little bit later, but for the time being, say that r is the distance from the point to the origin, and theta is the angle it makes with the positive x-axis. So we've seen this kind of description before. We'll use a lot of trig ideas in this lecture because we're dealing with, again, angles and distances to the origin. And it's not an exaggeration to say that this is another crucial topic for success in calculus. Calculus books have chapters on polar coordinates, and many objects in calculus are best described using polar coordinates. So it's important to get a feel for this new way of describing points in the plane. So here's my preliminary definition of polar coordinates. I'm going to make one modification a little bit later. Imagine a point xy in the plane. Here I've drawn a point xy, and it will also have polar coordinates r theta. And it's the same point, but two different ways of describing its location. We're very comfortable, I think, with Cartesian coordinates xy. Well, the polar coordinates, the r portion is the distance from the origin, 0, 0, out to the point. Now, on the picture, you see that it's directed distance, and you'll see what that means in a moment. And theta is the usual angle that you make with the positive x-axis. So those are the polar coordinates of a point. And using that definition, we can describe the location of points using their polar coordinates. Let me show you some simple examples of how easy it is to plot a point in polar coordinates. This is not difficult. Suppose you're given the polar coordinates of a point, r theta, and I like to put r theta there, and suppose the coordinates are 2, pi over 3. That means that r is 2 and theta is pi over 3. Well, think about what that means. Well, this point, wherever it is 2 units away from the origin, that's what r is, and it makes an angle of pi over 3 with the positive x-axis. So here could be a picture of that point. There it is in the first quadrant, 2 units away from the origin, and it's making an angle of pi over 3, isn't it? So that's kind of nice. Let's do another example. Here the coordinates are r theta equals 3, minus pi over 6. Okay, again, this point is 3 units away from the origin, and it makes an angle of minus pi over 6. That's a negative angle. Remember about those coterminal angles? Minus pi over 6 is coterminal with 11 pi over 6. So you could describe this point a couple of different ways. You could say its coordinates are 3 minus pi over 6 or 3, 11 pi over 6. Both yield the same point, a point that is 3 units away from the origin and making that angle with the positive x-axis. So there it is down there in the fourth quadrant. All right, let me make some comments about polar coordinates. In the first place, going back to rectangular coordinates or Cartesian coordinates, the xy coordinates, those are unique in the sense that every point in the plane has a unique set of rectangular coordinates. So things are pretty nice when you're doing xy coordinates. That's not true for polar coordinates. In fact, in that previous example, we noticed that we could change the angle by adding 2 pi and get an equivalent representation of the same point. In fact, it can be a lot worse. Imagine the origin. In Cartesian coordinates, it's 0, 0. All right. What is it in polar coordinates? Well, r is 0, and theta can be any angle you want. So there's an infinite number of representations for the origin. And it gets even more interesting. When you study polar coordinates, you're allowed to have r become a negative number. R can be negative. That's what we meant when we said directed distance. Let me show you an example of what I mean where r can actually be negative. And this is very useful when you're plotting curves using polar coordinates. So here's the example we'll look at. Let's consider the point whose polar coordinates are 3, 5 pi over 4. Let's think about that point for a moment. 3 units from the origin, that's the r value, and it makes an angle of 5 pi over 4. So where is it? 5 pi over 4, third quadrant. So another way of describing that point would be 3, minus 3 pi over 4. That would be going the other way, and we're still in the third quadrant. But there's a third way. And this is, imagine it this way. Instead of going 5 pi over 4 down that way, go angle pi over 4. That's the opposite direction. And then go minus 3 units. So you go down to the same point. So mathematically speaking, the representation of that point can be in many forms. And one of them is minus 3 pi over 4. Here's a picture of that point. Let me try to explain that minus r one more time. Imagine going angle pi over 4 from the origin. So you're looking at angle pi over 4, but instead of marching 3 units that way, you go back 3 units, and you'll end up at the same point we had before. Isn't that neat? Instead of going out 3 units, you go back 3 units, starting from the origin at angle pi over 4. So the bottom line is negative r values are permitted. It's not going to be something that upsets us, don't worry, but just to keep it in mind if you happen to read a textbook on polar coordinates. All right, we know how to do xy coordinates. We kind of understand these new polar coordinates. How do you go back and forth? How do you convert from one system of coordinates to the other system? Well, let's develop some equations that relate the two systems. And the good news is these equations all go back to our knowledge of trigonometry. So let's imagine the following scenario. We have the point P, and its coordinates are xy or r theta. And it's the same point in Cartesian coordinates, rectangular coordinates, or in polar coordinates. What kind of relations can we develop from this diagram? Well, remember the definition of the cosine function. Cosine theta is adjacent over hypotenuse, so it's x over r. So immediately, because cosine is x over r, x equals r cosine theta. And in the same way, sine theta is y over r, so sine theta, so y then becomes r sine theta. So now we have the conversion formulas. If I give you a point in r theta coordinates, in polar coordinates, all you have to do is plug it into these equations and out pops x and out pops y. X is r cosine theta, y is r sine theta. So that's pretty easy. Going from polar coordinates to xy coordinates, pretty easy according to these equations. That's the definition of the trig functions, isn't it? Going backwards, a little bit tougher. And here are some of the relations that will aid you in going backwards, and then we'll do some examples. For example, here, tangent theta is opposite over adjacent, y over x. So that gives a relationship between theta and y over x. And also, the distance to the origin, r squared, or the distance squared, is x squared plus y squared. So again, if I give you the xy coordinates, you can use these two equations, tan theta equal y over x and r squared equals x squared plus y squared, to try to figure out what r and theta is. But notice those equations aren't quite explicit, are they? They don't say theta equals or r equals blah. They don't say that. They're kind of embedded. So it's a little more work. Let's do some examples. How about r theta equals 2 pi, 2 comma pi. So r is 2 and theta is pi. Let's convert it to Cartesian coordinates. Well, piece of cake. X is r cosine theta. That's 2 cosine pi, because r is 2 and the angle is pi. 2 cosine pi, well, what's cosine pi? Cosine pi is -1, so the x-coordinate's -2. What about the y-coordinate? R sine theta. That's 2 sine pi, or 0, because sine of pi is 0. So the xy coordinates are -2, 0. In a minute, I'll plot that point, and we'll look at it a little closer. But let's do a second example. How about if r theta is, say, the ordered pair square root of 3, pi over 6? So the distance to the origin is square root of 3, and the angle it makes is pi over 6. What are the Cartesian coordinates? Well, r cosine theta would be square root of 3 cosine pi over 6. And now I have to pull that trig knowledge, don't I? A lot of trig coming into play here. Cosine of pi over 6 is square root of 3 over 2. And if you multiply those together, you get 3/2. What about y? Y is r sine theta. So it's square root of 3 sine pi over 6. Sine of pi over 6 is 1/2. And so you get square root of 3 over 2. So the Cartesian coordinates, the rectangular coordinates, are 3/2, square root of 3 over 2. Here's a picture of the 2 points we just analyzed. The first one was r theta equals 2 pi. Notice that point is 2 units away from the origin, and it makes an angle of pi with the positive x-axis, doesn't it? And its Cartesian coordinates are -2, 0. And the other point was square root of 3 pi over 6. Notice how it makes an angle of pi over 6, and its distance to the origin is square root of 3, and then we calculated the Cartesian coordinates. So I think that direction is pretty straightforward. Before we go the other way and convert the other direction, let me make a study tip here of something useful that I recommend my students always do. If you're dealing with polar coordinates or rectangular coordinates and you're working with them, tell the reader, tell your friends what coordinates you're dealing with. For example, if I write down the ordered pair 2 pi by itself, 2 pi, 2 pi, it's not clear what coordinate system I'm working with, is it? How could that be the xy coordinates of a point or the r theta? It could be either one, couldn't it? Now, of course, with a pi, you would sort of think that's probably an angle, but it could be the y coordinate of some number, of some point. So I suggest you say r theta equals 2 pi. And then everybody, oh, that's polar coordinates. And then xy is -2, 0. That tells me, yeah, it's the Cartesian coordinate system -2, 0. So put in front which system you're using when you write down an ordered pair. All right. I promised we'd go the other way in coordinate conversion. So here's a typical example. Suppose the Cartesian coordinates of a point are -1, 1. What are its polar coordinates? And again, these won't be unique, will they? A point has many, many polar coordinate versions. All right, so xy is -1, 1. Ask yourself, first of all, where is this point? In what quadrant? Well, x is negative, y is positive. That's in the second quadrant, isn't it? And what kind of angle does it make with the positive x-axis? Well, we can use that formula, tangent theta equals y over x. That's one of the conversion formulas. And that would be 1 over -1 or -1. Tangent theta equals -1. Here we are solving one of these trigonometric equations. You couldn't use the inverse. You could use the inverse tangent function here maybe, but just think about it. Can you find an angle theta whose tangent is -1 and it's living in the second quadrant? That's right, 3 pi over 4. The tangent of 3 pi over 4 is -1, and 3 pi over 4 is in the second quadrant. So now I know theta. What about r? Well, r is somewhat easier. It's x squared plus y squared square rooted. So r squared equals -1 squared plus 1 squared, which adds up to 2. And so r is the square root of 2. Okay. The polar coordinates are r theta equals square root of 2, 3 pi over 4. Here's a picture of the situation. We started off with the Cartesian coordinates, -1, 1, and we saw that it's in the second quadrant. There it is. And now the polar coordinates tell us how far that point is away from the origin. Its distance is square root of 2. And of course, it makes an angle of 3 pi over 4. That said, you know there are other ways of writing this answer, aren't there? You could write it as minus square root of 2, 7 pi over 4. Think about that. Start at the origin and spin around to an angle 7 pi over 4. You'll now be in the fourth quadrant. But go backwards. Go backwards minus square root of 2, and you'll end up at the same point. So that's another version, and of course there's an infinite number of versions for this point. I said it's more difficult to convert from polars to rectangular. There's no doubt about that. It's more difficult to convert from rectangular to polar. Sorry about that. It's more difficult to go, like in the previous example, from -1, 1 over to its polar coordinates. The good news is when you get your answer, you can always check it by going the other direction. You can sort of go backwards again and see if you really got it right. Okay, I hope we're comfortable now with polar coordinates, converting back and forth. Let's look at some polar equations, and you'll now see some of the richness of this field and some of the real advantages of using polar coordinates over rectangular coordinates in certain situations. For instance, describe the polar equation r equals 2. R equals 2. What's that look like? What's the graph of r equals 2? Well, first of all, notice that theta is not even there. So theta can be any angle. Theta is free to roam around any angle it wants. And the distance to the origin is always 2 units, isn't it? What is that? A circle. It's the circle of radius 2. Now, if you're uncomfortable with that, convert to rectangular coordinates. If r is 2, squaring it, r squared is 4, and remember the conversion formula, r squared is x squared plus y squared. So we end up with x squared plus y squared equals 4, which we know in our heart is a circle of radius 2. But notice something curious here. That circle in Cartesian coordinates is not a function, is it? It's hard to graph that in a graphing calculator, say, because you'd have to solve for y and have 2 equations. But r equals 2 is a very simple function, isn't it? It's a constant function in the polar coordinate system. So in polar coordinates, circles are pretty easy to describe. Let me show you another easy curve to describe. What does theta equal a constant look like? Say pi over 3. So now theta is fixed at pi over 3, and r is any value it wants. What do you think this is going to be? Well, before I convert to Cartesian coordinates, imagine you go angle pi over 3, and then you can go up and down that angle because there's no restriction on r, is there? R can be positive or negative. But let's go ahead and convert. Remember the formula, tangent theta is y over x, so tangent of pi over 3 is y over x. Tangent of pi over 3, what is that? That's the square root of 3. And so I get square root of 3 equals y over x, or y equals square root of 3 times x. That's a straight line, isn't it? That's a line of slope, square root of 3, y-intercept 0. Here it is. There's the line y equals square root of 3x. And notice that it makes an angle of pi over 3, doesn't it? So that's kind of a neat way of describing a line. You just give its angle, and bingo, you got the line. All right, you're the teacher again. Student comes running up to you. Professor, I remember that vertical lines are not functions. In fact, a vertical line does not pass the vertical line test. Can we still describe a vertical line in polar coordinates? How would we do that, teacher? Well, let's think about it. Let's do a specific example. Let's take the vertical line x equals 1. That's a vertical line. It touches the x-axis at 1. Let's convert that to polar coordinates. All right, well, what's x? X is r cosine theta. So r cosine theta is 1. Divide by cosine. R is 1 over cosine, which also goes by the name secant. So the function r equals secant theta describes a vertical line. Isn't that cool? As theta varies, you go up and down that vertical line, x equals 1. Here's a picture of that line. It's a vertical line, and we've described it both in Cartesian coordinates and in polar coordinates. Let me make a comment that we've sort of alluded to earlier, a calculus comment, that many of these curves that we have been using, like circles and things, are not functions. They don't pass vertical line tests. But with polar coordinates, it's much simpler to describe them. Suppose you wanted to graph on your calculator x squared plus y squared equals 9, a circle of radius 3. Well, in Cartesian mode, you'd have to divide that up into two pieces, the semicircle on top and the semicircle on the bottom. So you'd solve for y. Y is plus or minus square root of 9 minus x squared, and then you would graph two pieces. Y equals square root of 9 minus x squared, and then minus the square root of 9 minus x squared, and that would yield the two semicircles. But your calculator has polar mode built into it. Aren't these engineers amazing with the calculators? All the topics we've talked about in this course are built into our calculators. It's as if they were listening to mathematicians and scientists and said, oh, what do you want on your calculator? And they provided it. They have parametric mode and they have polar mode. Okay, so if you go to polar mode, you'll be graphing curves in polar coordinates. And this one would be pretty easy. It's r equals 3, a circle of radius 3. You would just type in r equals 3 as your curve, and the circle would appear on your screen. It's amazing. If I had a new job, I would work for a calculator company. I think they do really amazing things with those little devices. Okay, let me show you a really fun example now about polar coordinates, a really neat curve. Up to now, we've been looking at some fairly simple ones, a straight line, a circle. Well, here's a more interesting equation. R equals 4 sine theta. What will that look like if I plot it? If I graph that, say on my graphing calculator, what will it look like? Well, you could point plot it. Remember, graphing calculators are nothing more than point plotters. They just take a lot of points and plot them. Well, let's do a few by hand. We're much slower than a calculator, but let's get a feel for it. How does this work? Well, you pick certain theta values, and then you compute the corresponding r value, because r is a function of theta. So when theta is 0, r is 4 sine 0, so r is also 0. When theta, say, pi over 4, r is 4 sine pi over 4. Sine of pi over 4 is square root of 2 over 2, so r is 2 root 2. So whatever this curve looks like, it starts at the origin, and then it goes out a distance 2 square roots of 2 when the angle is pi over 4. All right, what happens when theta is pi over 2? Plug that in. Sine of pi over 2 is 1. Suddenly I'm up here at distance 4 from the origin. R is 4, and pi over 2 makes me on the y-axis. It puts me on the y-axis. And now how about if theta's pi? If theta's pi, plug it in, sine of pi is 0. Whoa, I'm back at the origin again. And then you could plug in a lot more points, pi over 6, pi over 3, your favorite values, because you know a lot of trig values for common angles. And you would get a picture like this. Kind of surprising, isn't it? It's another circle, but it's been moved up the y-axis, hasn't it? Here I've plotted when theta is 0, we're at the origin. When theta is pi over 4, we're at an angle of pi over 4, and we're at a certain distance from the origin. And then up there at 4 was when theta was pi over 2, and then it comes back down again. It's a circle. Let me convince you that it's really a circle by eliminating the parameter. This is kind of a fun process for this example. I think you'll like some of the tricks involved. Okay, I want to take the function r equals 4 sine theta, and I shouldn't say eliminate the parameter. I want to convert it to Cartesian coordinates. I want to eliminate the theta and eliminate the r. I want to get it back to Cartesian coordinates. Here we go. R is 4 sine theta, and the first trick, and you'll see why I do it, multiply both sides by r. Watch what happens. What happens to the r times r? That's r squared. Oh, r squared is x squared plus y squared. That's one of the conversion formulas, isn't it? That's the distance to the origin squared. And now on the right, I see 4r sine theta. Oh, wait a minute. R sine theta is y. That's one of the definitions. Y is r sine theta. Y is r sine theta. So the right-hand side is 4y. And now, hey, I've eliminated the r and the theta. I'm back to x's and y's. But it's not quite clear what that equation describes, is it? So bring the 4y over to the other side, and let's complete the square. So we get y squared minus 4y plus something. And remember the rule, you divide by 2 and square it. 4 over 2 is 2, squared is 4. So I add 4 plus x squared, and then I add 4 on the other side so I don't change the problem. And now I have a perfect square, y minus 2 quantity squared plus x squared equals 4. Who's that? What is that? Oh, that's a circle. The center is at 0, 2, isn't it? And the radius is 2. Look back at the picture. Where's the center? 0, 2. What's the radius? 2. Isn't that neat? That fairly complicated equation turned out to be a circle that's been moved up the y-axis a couple of units. Now, the field of polar coordinates goes on, and one of the really interesting parts of it for me is that polar equations give rise to really interesting and beautiful graphs. Let me show you a couple of graphs, and then I invite you to try some more with your graphing calculator. These are hard to graph by hand. A lot of point plotting is necessary, but your graphing calculator will do it quite quickly, and they're fun to look at and to play with. So here's one that's kind of appropriate for Valentine's Day. Try plotting 5 minus 5 sine theta. This is called a cardioid. And I've graphed it on the screen from minus 9 to 9 for the x coordinates and minus 10 to 2 for the y coordinates. And theta went from 0 to 2 pi, and it traces out this very pretty Valentine. Isn't that nice? Heart-shaped curve. Here's another one you could try. 6 sine 2 theta. Try graphing that. You should get a rose type, a flower like this. It's a 4-leaved rose, they call it in this business. And you might ask yourself some questions, and you can answer them by exploring on your own. What does the 6 mean in this equation? R is 6 sine 2 theta. I think I said 2 theta here. 6 sine 2 theta. What does the 6 describe? Well, that's sort of how far out the leaves go from the origin. But what about that 2 theta? Isn't that interesting? The 2 theta gave rise to 4 leaves. What do you think 4 theta will do? Or 6 theta? Or 3 theta? Instead of 2 theta? Try it for yourselves and you'll get some surprises. There are many, many curves. Our workbook will have a few examples also that you can look at. But make sure you set your calculator to polar mode, and I recommend definitely radian mode for all of this. And just keep in mind that your calculator is doing what you could do if you had a lot of time, meaning it's point plotting. Okay, let me show you one more. This is really a great curve, and there's a whole family of these curves. This is r equals 15 over 3 minus 2 cosine theta. Okay, whoa, what a bizarre curve, right? Let me graph this for you, and this will be an old friend. Wow, it's an ellipse. Isn't that neat? But it's an ellipse that's been kind of shifted. It's not at the origin, is it? The center's not at the origin. And if you go back to that equation and change the 15 to a different number, or change the 3, or change the minus sign to a plus sign, or change the 2, change cosine to sine, you'll get all kinds of really interesting curves. In fact, some of them will turn out to be hyperbolas, and some will be parabolas. In fact, all of those conic sections can be described with formulas that kind of look like this one. So you see there's a whole world out there for you to study later on. Okay, what are we going to do next time? We're going to completely switch gears. We're going to go down a whole new path. We're going to talk about a subject that's very appropriate for calculus, especially calculus in the second semester or in the advanced placement BC version. That said, these ideas are, again, used in pre-calculus courses all the time. We'll talk about two different topics. One is sequences. Here's a sequence. It's a string of numbers, 1, 1/2, 1/3, 1/4. That's a sequence of numbers. And one of the most famous sequences that we'll look at is the so-called Fibonacci sequence. And then we'll talk about series. And series is adding up the terms of a sequence. In other words, I'm going to add 1 plus 1/2 plus 1/3 plus 1/4, etc. What does that add up to if I go out to infinity? Not clear, is it? So tune in next lecture when we talk about sequences and series. Thanks.